Welcome. So this problem says a 4 kilogram object hangs from a force gauge while traveling in an elevator that is moving upwards and speeding up. Its acceleration is 3 meters per second squared. What is the apparent weight indicated by the gauge, the spring scale, whatever, this guy up here? Look at this diagram. We have, of course, a weight downwards, so we have a 40, and this of course pulls with a tension on the string, and the string pulls down with a tension on the gauge, and it is this tension which the gauge reads. It records how forcefully it is pulled. So, and what happens is, under different acceleration circumstances, the amount of this pulling can change. The classic case is getting in an elevator, and you can feel it when you begin to accelerate as you're traveling upwards. So the acceleration is up and the velocity is up because you're speeding up on the way up. You kind of feel your knees buckle a little bit. And then when you get to the end of your journey and you slow down, so the acceleration is downwards, but you're still traveling upwards to your floor, then you tend to feel a bit light-footed. You tend to rise a little bit. And that's the effect that we're looking at, your apparent weight changes. So what we can say is, let's draw ourselves a diagram of this object. So here's the object, and it's 4 newtons. And what counts is that we have a weight on here, which is a pull of gravity, which is 40 newtons. We have a tension upwards, which is going to be equal to our apparent weight. This is what we want. But the fact is, we're not in equilibrium. We are accelerating. And what it says is that the object is moving upwards and speeding up. If I'm moving upwards, my velocity is upwards. If I'm speeding up, that also means my acceleration is upwards, because when the velocity and the acceleration are in the same direction, then you're speeding up, and when the velocity and the acceleration are in opposite directions, you're slowing down. So this is a value of 3 meters per second squared. But the important thing is that this is pointing upwards. So there's my diagram. And I say to myself, oh, well, okay, let's apply Newton's laws. The sum of the forces vertically must equal, well, it's accelerating, so it must be equal to MA. If you like, MA vertically as well. So we can look at our diagram, and we can say plus t, because that's pointing upwards. Let's make this the positive end and this the negative end. The same skills we've had, for many questions. So that's plus t added to minus 40 is equal to 4 times through our discussion of velocity and speeding up, we know that this is a plus 3. So then we say, oh, in that case, then our t is going to equal 12. 3 fours are 12 plus 40. So t is going to equal 52 newtons. And it is here. I'd like to extend this just a little bit and say, what would have happened if, let's draw a line here, what would have happened if the acceleration had been, if the measurement had been taken while the object was moving upwards and slowing down? Well, in that case, I'm going to truncate my diagram a bit. We would still have a t upwards, and we'd still have 40 downwards, because the weight is the weight. We're not moving where we are, we're just changing our acceleration. If we were still moving upwards, but now we were slowing down, this acceleration would have to be minus 3 meters per second squared, because these two cannot point in the same direction. The acceleration must be in the opposite direction of the velocity if I'm slowing down. So then I can say, oh, well, it's still the same rule. The sum of the forces vertically is equal to the mass times the vertical acceleration. And in this case, I would say plus t added to minus 40, it's still pointing downwards, is equal to 4 times, but in this case it would be minus 3. So then I would say, well, in that case then t is equal to minus 12 added to plus 40. So t would equal 40 minus 12, 28 newtons. It would appear to weigh less while the elevator is slowing down on the way upwards. So we'd have a different answer on there. So really the trick with this is to be able to interpret from the words a visualization, and specifically not making a mistake about the actual sign given to the acceleration. The only other thing that was a little bit awkward about this one is apparent weight. If you didn't pay attention, you might not remember or recognize that the apparent weight is equal to the actual tension that the spring gauge is, the force gauge is pulled by. The weight is equal to the tension that the force gauge is pulled by, and that the apparent weight is this apparent different weight which is caused when your system, the block and the gauge, are accelerating. So there we have it.